Hello, Lower 6 mathematicians. This is a video about the geometric distribution. Please feel free to stop it as and when you want to make notes, or if you want to ask questions, then pause it, put your hand up, and I'll come and answer them. Okay, so first off, let's just recap what we know already about the geometric distribution. So first off, there are only two outcomes in the geometric distribution. There's success, which I will always give the letter P to denote the probability, so small p, and failure, which I will give Q to denote the probability of failure. And as we know, if we sum Q and P together, so P plus Q must equal 1. So you can either have only success or failure. Just on that point, with regards to there only being success and failure, if, for example, my experiment was to roll a die, now there are obviously 6 outcomes that you could get, but when we talk about geometric distribution, we have to stipulate what is a success. So I might say that rolling a 6 is a success, and everything other than that is a failure. So that's where I get my only options being success and failure as my outcomes. So small p for success, small q for failure, p plus q equals 1. Next thing that I know already about geometric distribution, you keep repeating the experiment until you get a success, and then at that point you stop the experiment. There's no continuation of what you do. At the point of success, you stop. So anything leading up to a success must be a failure, by definition. So they are the two things that we know already about the geometric distribution. Just a quick reminder of the notation of the geometric distribution. So I've got a random variable x, and that's got a geometric distribution. So how I show that is so geometric, GEO, and then in brackets, that's the probability of success. So that is how I would show the notation I would use for the geometric distribution. Okay, so let's think of an example. So let's say that my random variable x is that I roll a die, and I get a 6. So that is what the random variable x is. The success, i.e. the success, is that you roll and you get a 6. So the value of p must be equal to 1/6, and the value of q must be equal to 5/6. So before I've even entered into the question, I have written out my value of p and my value of q, because that's probably going to be helpful a bit later on, and it's quite helpful just to have it there already done. So if I were to just go back and write it like this, in this notation, it would be random variable x has a geometric distribution, and then the 6 goes in brackets. Okay, so if you remember before the notes that we made about the geometric distribution, you will hopefully remember this formula. So the probability that x is equal to some number, which I'm going to give small x to, is equal to q x minus 1 times p. If we go do an example, that will help us to understand this a little bit more. So let's say that probability that x is equal to 5. So think about what that means. That means that what is the probability that it takes me 5 attempts to roll a 6 on a die? Now, because of this condition, everything up to just before the 5th attempt, i.e. the 4th attempt, everything up to that must have been a failure. So I would have had to have rolled failure, 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 and then I roll a success, i.e. I roll a 6. So failure on the first roll, failure on the second roll, failure on the third roll, failure on the 4th roll, and then success on the 5th roll. So if I just shorten that down, So let's just go back to this equation here and how they are associated with each other. So Q is the probability of success of failure, so that's going to be 5 over 6 to the power of x minus 1. Well, if x is 5, that means on the 5th attempt I get success. So I will have to have rolled 4 failures before that. So that's 5/5 to the 4, and then on the 5th attempt I roll my success. So if I do that on my calculator, so if you do that on your calculator, you should get so if I round it to 3 significant figures, that's the probability. Okay, so that's how this formula works, which we've covered before. So remember, so it's failure to the power of x minus 1 times by probability of success. So remember that I'm doing this using a formula, but I could have done it on a tree diagram. There isn't anything wrong with that, but as we'll come to see a bit later on, it's pretty inefficient and it will take a long time. But if we just sort of go back to having a look at a tree diagram, then hopefully that will sort of help our understanding a bit more. So when we are rolling the die, we either get a success, i.e. rolling a 6, or a failure, which is when I don't roll a 6. And if I get a failure, I carry on going. So on the first roll, I would either get a 6 or not a 6. So the probability of getting a 6 is 1/6. The probability of not a 6 is 5/6. If I got a 6, I would stop. But here, I carry on going. So that's the first roll. The second roll, I either get a 6 or I don't get a 6. If here, I would stop. So that would be not 6 or failure, success. But here, I keep on going because it's a failure again. So I could get a 6 or not a 6. So if I here stop, keep going, 6, not a 6, just carrying on filling in, 6, not a 6. So this is the point here that corresponds to this question up here, because you've got first fail, second fail, third fail, fourth fail, and then you get your success. But actually, this tree diagram can continue on forever and ever and ever, couldn't it? Because there is a very, very small chance that you could roll 10 times, 300 times, 2,000 times before you get a 6. It would be very unlikely that you don't have a 6 by the 2,000th attempt, but in theory it is possible. So this tree diagram could go on forever and ever and ever and ever, because in theory you might not get a 6. So yes, we could use a tree diagram, but as I said before, it's not particularly efficient and it's better to use the formula. But hopefully the tree diagram shows you a different idea about where the formula comes from. Using a tree diagram can also be helpful to introduce another geometric distribution idea. So in order to help us with this new idea, I want to take a completely different situation, completely different bit of probability, which has got nothing to do with the geometric distribution, because I just want you to remind you of the idea that we're going to come to. So imagine that I have got a bag of beads, and in my bag I have got 2 red beads and 3 blue beads. So this is something that you will have done back in, I don't know, year 8, year 9, about probability. So none of this will be new, but I just want to remind you of a concept because we're going to go back to that a bit later. So imagine the situation where you pick a bead, you look at the colour, you replace the bead, and then you pick another bead. Okay, so you're picking 2 beads, with replacement. What I want to do is I want to have a look at the combinations that you could get and also their associated probabilities. So on the first pick, you could get a red bead or a blue bead. Probability of a red bead is 2/5. Probability of a blue bead is 3/5. Remember, you put the bead back, so on the second pick, I could get a red bead or a blue bead, 2/5, 3/5. And having picked a blue bead to start with, on the second pick you could either get a red bead or a blue bead. So remember, this has got nothing to do with the geometric distribution, it's just a concept which I want to remind you of. So, what have we got here? Our outcomes are red, 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 blue, blue, red, and blue, blue. Okay, so what's the probability of red, red? Well, you just times these together. So that would be 4 out of 25. So that's 2/5 times 3/5. So that's 6 out of 25. 3/5 times 2/5. 6 out of 25. And 3/5 times 3/5. So that's 9 out of 25. Okay, so nothing new about that. But the key thing that I want to remind you of here is that all of these probabilities here add up to 1. Okay, so 4, 10, 16, 25. So that's 25 out of 25. So all of these probabilities here add up to 1. So, with this in mind, I want to let's just go back to this tree diagram that we did here, which I said went on forever. So even though it keeps on going forever and ever and ever, it will. So all of the outcomes, which I sort of could write down here. So if you think about, well, what outcome did I get first? I got success, then I got failure and success, and then I got failure, failure, success, failure, 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 success, failure, 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 success, and then it could go on, couldn't it? Because, what's that? So that will be, it just keeps on going on. But they all add up to 1, even though it goes on to infinity. You'll come, just to link in with core, you'll come to the idea of summing to infinity in due course in your core maths. So just sort of bear that in mind when you're looking in core at summing to infinity in your core lessons. So, key idea from this is that all of these outcomes, even though they go on forever and ever and ever, will eventually add up to 1. Because of this idea that we've introduced here, where all of the probabilities must add up to 1. So instead of representing it on a tree diagram, I am going to think about, going back to the geometric distribution, I'm going to think about what I did here. I'm going to think about it in a slightly different way, and lay it out in a slightly different way. And I'm going to lay it out as sort of what might look like a number line. So I roll a die and I want to get a success of it rolling, rolling a 6. So again, that's my criteria. Rolling 6 is a success. So I could roll a 6 on the first go, on the second go, third go, fourth go, 5th, 6th, 7th, 8, 9, 10, oh, it keeps on going, all the way up, well, to n really, isn't it? Because it keeps on going forever, any number, so it keeps on going. I know that all of these probabilities here have got to add up to 1. So they've all got their own separate probabilities. So the probability I roll it on the first go, so that's like this one here. Probability I roll it on the first go is a 6. So I'm just going to sort of jot these down up here. The probability I roll it on the second go, well, that must be failure first, and then success. On the third go, must be 2 failures, and then